self loop, self loop, self loop, okay, self loop, and parallel edges is also a tree. Is parallel edges, parallel edges, parallel edges, also a tree, also a tree, also a tree, also a tree, also a tree in which there is a designated vertex, a tree, a tree in which there is in which in which in which there is a designated there is a there is a designated designated vertex V naught, vertex V naught, vertex V naught, say with in degree, say with in degrees, with n degrees, n degrees, n degrees, in degrees, n degree, zero called the root, degree, zero called the root, zero called the root, zero called the root, and all other internal vertices and all other all other all other and all other internal vertices have internal vertices have all other vertices have in degree 1 in in degree 1 in degree 1 in degree 1 is known as a rooted tree, is known as a rooted tree, rooted tree. So rooted tree. Next, trees, forest and rooted trees. Definitions. Trees, forest and rooted trees. Forest. Page number 169. Forest and rooted trees. Rooted trees. Forest and rooted trees. Forest and rooted trees. Let G become my definition. 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 Let G become my G become my G become my be a simple group. Simple group. Be a simple group. The graph G is called the graph. The graph G is called. G is called. G is called a tree. G is called a tree. G is called a tree. If it is connected, if it is connected, if it is connected, it is connected and is without cycles, and it is without cycles, without cycles, without cycles, without cycles means nothing but loops. LOP, loops, loops. In other words, in other words, in other words, other words, a tree is connected a cycle graph. A tree is connected, connected, connected a cycle graph, a cycle graph, a cycle graph, a cycle. A cycle means not displaying or forming part of a cycle. A cyclic, a cyclic, a cyclic graph means say forming part of a cycle. Diagram. P naught. V1. Next. V1. V1. 1. V2. V2. V5. V5. V1. V3. V3. V7. Say V7. Page number 169. V7. V4. 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 V6. V6. V8. 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 This is graph 1. G1 consider. Next. One more graph. V6. V6. Next. V4, V2. V4. V2. V5. V8. 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 V5. V5. So this is consider G2. This is a graph. This is a tree. G1 is a tree, but it is not a tree. What is the reason? Not a tree. Here become, here observe, V0, V1, V4, V2, V1. It is a cycle or loop it happened. So it is a not a tree. Tree. Not a tree. Okay, one more definition. Definition. Not definition. Different. Definition. A graph GV, a graph a graph GV, IE, GV, IE is called a forest. Is called a forest. Is called a forest. If it is acyclic, if it is acyclic graph, acyclic, 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 acyclic. It does not contain any cycles. It does not contains any cycle. Any cycle. A cycle does not contain any cycle. Any cycle. Does a connected subgraph, does a connected subgraph, connected a subgraph, connected subgraph of a forest tree, of a forest tree, forest is a tree. So one more definition. Definition. A tree with a designated vertex, and tree with a designated vertex, with a designated vertex, designated vertex, we not called the root, called the root, called the root, we not called the root, is called rooted tree. It's called rooted tree. Rooted tree. It's called rooted tree. It's called rooted tree. Rooted tree. Is called a rooted tree. If each vertex other than V0, if each vertex other than V0, other than V0, has in degree, has has in degree, has in degree. That means V1, Vi equal to 1. And in degree, and in degree, in degree, V not equal to 0, V not equal to 0, V not equal to 0. As in degree, V naught is 0. V naught is 0. Next. Here is the partition. Discuss theorem, page number 172. Page number 172. Theorem. Theorem. In a tree, any two vertices in a tree, any two vertices, any two vertices in a tree, any two vertices are connected by are connected by connected by a unique simple path, a unique simple path, simple path, unique simple path, simple path. Proof. Proof. Let T be a non-trivial tree. Let T be a non-trivial tree. Non-trivial, non-trivial, trivial tree. Non-trivial tree. Non-trivial tree of the graph G of the graph G of a graph G graph G graph G and U comma V be any two vertices. Let U comma V be any two vertices of T. Any two vertices any two vertices of T. Any two vertices of T. Since T is connected, since T is connected T is connected. 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 There exists a path. There exists a path. There exists a path. Path. Say P1 from U to V. Say P1 from P1 from U to V. U to V. U to V. U to V in G. U to V in G. Okay. Suppose there is another path. Suppose there is another path. There is another path. Another path. Other path. Path. Say P2. Say P2. Say P2. From U to V. From U to from U to V. From U to V. U to V. In G. U to V in G. In G. Since P2 is not equal to P1. Since P2 is not equal to P1. P2 is not equal to P1. P2 is not equal to P1. There exists an edge E equal to. There exists an edge. An edge. An edge. An edge E equal to X comma Y. Equal to XY. Equal to XY. Where X comma Y is not equal to V. T which is in P2 and not in P1. Not in P1. Where? Not in P1. Okay. P1 and X. Where X comma Y. Where X comma Y. Where X comma Y is not equal to. Is not equal to. Where X comma Y is not equal to. Where X comma Y. X comma Y. X comma Y. Where X comma Y not equal to V of T. V of T not equal to T. Which is in P2. Which is in P2. Is in P2 and not in P1. And not in P1. Not in P1. Not in P1. Now P1 union P2. P1 union P2. P1 union P2 minus E. E is an X minus Y. Walk in T. Walk in T. Walk in T. So there is a X minus Y path. So there is a X minus Y path. There is X minus Y path. There is X minus Y path. X minus Y path. extra. Say P in T, path. Say P in T. Say P in T. X minus what? Say P in T. Then P plus E is a cycle in T. Then P plus E, P plus E is a cycle in T. Is a cycle in T. Cycle in T. Is a cycle in T. Cycle in T. And this contradicts the contradicts the contradicts and this contradicts the acyclic nature of T. The acyclic cyclic acyclic nature of T. Nature of T. Nature of T. Acyclic nature of T. Hence our assumption is false. Hence our assumption is false. Hence our assumption is false. Our assumption is false. Assumption is false. False. Hence the proof. This completes the proof of theorem. Means hence proved. One more theorem. A tree with n vertices. A tree theorem. Three theorem. A tree with n vertices, n minus h, nothing but it is a spanning tree. A tree statement. A tree with n vertices. With n vertices. N vertices. A tree with n vertices. A tree with n vertices. N vertices has n minus 1 edges. No, it means n is greater than or equal to 1. 1 has n minus 1 edges. Has n minus 1 edges. And edges. N minus 1 edges. Proof. We'll use mathematical induction. We will use mathematical induction. Mathematical induction. Mathematical induction. Put n equal to 1. Put n equal to a true with n equal to 1. A tree with n equal to 1. N equal to 1. Vertex has no edges. N equal to 1. Vertex has no edges. Vertex has no edges. Hence the result is true for n equal to 1. Hence the result is the result, and the result is true for n equal to 1, n equal to 1, true for n equal to 1, result n equal to true for n equal to 1. Let us assume that every tree with k vertices, let us assume that, let us assume that, let us assume that, assume that, assume that every tree with k vertices, every tree with k vertices, k vertices k vertices with k vertices, every tree with k vertices has k minus 1 edges, has k minus 1, k minus 1 edges, k minus 1 edges, k minus 1 edges, where k is greater than is finite, where k greater than 1 is greater than 1 is finite, is finite. K1 is finite. Suppose the tree T has k plus 1 vertices. Let T has let T has k plus 1 vertices. T plus 1 vertices. K plus 1 vertices. And that V is a leaf of T. And V is a leaf of leaf of leaf of T. Leaf of T. And W be the parent of V. Hmm? W be the parent of V. Parent of V. W is the parent of V. Removing from T the vertex V, removing 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 from T the vertex, from T the vertex from the vertex to the vertex V, and the edge connecting W. Hmm. Edge connecting W. Edge connecting edge connecting W to V. W to V, W2V, produces a tree T dash, produces a tree, T dash, with K vertices, with K vertices. K vertices, the K vertices. Since the resulting path, the resulting graph is, since the resulting resulting since the resulting since the resulting graph is still connected and has no simple circuit in graph, still connected, still connected, still connected, still connected, and has no simple circuits, and has no simple circuits, and has no simple circuits, no simple circuits, no simple circuits, no simple circuits. Then by induction hypothesis, then by induction hypothesis, then by induction, then by induction hypothesis, then by induction hypothesis, then by induction hypothesis, K minus T dash has K minus 1 edges, T dash has K minus 1 edges, K minus 1 edges, K minus 1 edges. It follows that T has, it follows that, it follows that, it follows that, it follows that, it follows that T has, T has K edges, follows that T has K edges, T edges, follows that T has K edges. Since it has one more edge, since it has one more edge, one more edge, one more edge, one more edge, T dash the edge connecting, T dash the, T dash the, one more edge, T dash the edge connecting, the edge connecting, edge connecting, edge connecting V and W, V and W, V and W. Thus completes the induction step. This completes the proof, hence proof. Hence proof. Right. Right. Page number 174. Definition. 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 A rooted tree is called. This is not the problem. Check. Definition. A rooted tree. Binary trees and their traversals. Binary tree. Binary. Binary trees. Binary tree. Right. And their traversals. And their traversals. Traversals. Binary tree and their traversals. Binary tree and their traversals. A rooted tree is called a rooted tree is called a rooted tree is called MRA tree. MRA MRA tree. MRA tree. If every internal vertex has no more than if every internal vertex has every internal vertex has no more than m children. No more than m children. M children. A tree is called a full MRA. A tree is called a tree is called a full MRA. Called a full MRA. 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 Tree with m equal to 2. With m equal to 2. M equal to 2. MRA. Every internal vertex has exactly m children. 2 is called binary tree. Called binary tree. Binary tree. Binary tree. Next. Definition. Traversals. Definition. DEFN means definition. Procedures for systematically procedure For systematically visiting systematically visited systematically visiting every vertex, visiting every vertex, visiting every vertex, every vertex, visiting every vertex, visiting every vertex, visiting every vertex of a binary tree are called of binary binary tree are called binary tree are called binary tree are called traversals algorithm traversals traversals algorithm means step by step procedure is called algorithm algorithm algorithm. Here one more important theorem for theory 10 marks question. We'll discuss theorem. 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 The maximum number of vertices. The maximum number of vertices. Number of vertices. Number of vertices. Maximum number of vertices possible in a binary tree. 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 Of height n is of height or length. Height n is 2 to the power of n minus 1. Most important for theory 10 marks question. Proof. So for n equal to 1, we have for n equal to 1. N equal to 1. We have 2 to the power of n minus 1. 2 to the power of n minus 1 is nothing equal to 1. So which is obviously the root vertex of binary tree. Which is obviously obviously which is obviously the root vertex of binary tree. The root vertex of binary tree. Binary tree. Root vertex of binary tree. Root vertex of binary tree. Root vertex of binary tree. Suppose the result is true for n equal to k. This is also we are using by mathematical induction we are proving. let the result is true for the result is true for result is true for n equal to k, n equal to k. The maximum possible number of vertices of k to the power of k. By induction hypothesis, we obtain by induction hypothesis induction hypothesis, we obtain 2 to the power of k minus 1 to the power of k minus 1. Third step, let assume it to be true. Let n equal to k plus 1 is assumed to be true. So then 2 to the power of place of k, we are substituting 2 power k plus 1 minus 1. That can be written as 2 to the power of k into 2 power 1 minus. Since each vertex is binary, since each vertex since each vertex since each vertex in a binary has in a binary tree has binary tree has at most two children, at most two children. At most two children. Yeah. At most two children. The maximum number of vertices at a particular height. The maximum number of maximum number of vertices of a particular height. Vertices of a particular height. Particular height. Particular height. Particular height. Particular height. Particular height. Particular height is twice the number of vertices. Is twice the number of vertices. Number of vertices. Number of vertices. Number of vertices at the preceding height. At the preceding height. The preceding height. At the preceding height. Hence 2 to the power of 2 to the power of k plus 1, 2 to the power of k plus 1, that equal to 2 into 2 to the power of k, 2 into 2 into 2 to the power of k, 2 to the power of k minus 1. Okay. Hence the result is true for integer n. Hence the result is true for n. True for n. Okay. Here in this one, most important theorem, page number 175. Page number 175 is 10.4.5. And one more 10 marks question. So page number 181. Page number 181. Kruskal's algorithm. Kruskal's algorithm for 10 marks question. Kruskal's algorithm. Algorithm. And page number 182. Prim's algorithm. Page number 182. Prim's algorithm. Prim's algorithm based upon these problems. 3 are theory 10 marks question. Theory 10 marks question each. 10 marks questions. So what we discussed, basic